I'm Ellie Taylor-Brewin, and this is Oliver Ukereghe, and we are MajorTim.space Young Ambassadors. Today we are delighted to be interviewing Dr. Kirby Runyon. Kirby, could you please introduce yourself?
Sure, I'd love to talk to you. Thanks for talking to you, Ellie and Oliver. So I'm Dr. Kirby Runyon. The main thing you need to know about me is that I'm a giant space nerd. I love exploring space, and I pursued that passion. I am now a staff scientist in planetary geology, studying the rocks and the rocky landscapes on other planets and moons. And I'm employed by the Planetary Science Institute, and we receive NASA funding here in the United States to basically explore space. I also run my own company called Planetary Experience, and Planetary Experience is really devoted to helping people have fun learning about space. So it sort of combines space education with space entertainment. And so as a scientist, I study the rocky landscapes on the moon, on Mars, even on places like Pluto, which I think is still a planet. And I understand how different geologic forces have shaped the beautiful alien landscapes we see across the solar system. But I'm a public speaker. I love just getting people excited, getting them informed with an informed enthusiasm about space exploration.
Thanks. What inspired you to pursue a career in planetary science?
Yeah, thanks. I don't know what got me interested in space in the beginning. Growing up in southern Michigan in the United States, my parents took me to the Michigan Space and Science Center that had a number of flown space artifacts. And it was in my high school years and that I really realized that I wanted to go get a doctorate, get a PhD in science, in space science. At the time, I thought that would be astrophysics because I didn't know of any other space sciences. I just only knew of astrophysics. I had also thought about maybe going into engineering, like being the type of person who builds spacecraft or builds instruments to go to space. But I really realized that I wanted to study the cosmos itself more than, and I would let other people build the things that take us there. And so I majored in physics in university. I could have majored in something else. I probably could have majored in geology or astronomy or even something like chemistry or biology, but I chose physics. But I am actually quite bad at math, and I wasn't going to be able to really hack it with astrophysics. But I discovered along the way that the scientists working on like the Mars rovers or on the Cassini orbiter that ESA and NASA worked together on to orbit Saturn, it was flying by all these moons. A lot of these scientists were geologists. And I thought geologists just studied Earth, but geologists study any time that there's a rocky landscape. And so a lot of these scientists are actually planetary geologists. So towards the end of my undergraduate years in university, I decided to go for a master's degree and a PhD in planetary geology, partly because there's less math, but also just because it's more tuned to how my brain works. My whole life is trying to answer the question, what is it like in space? I'm a very visual person. And so one way to answer the question, what's it like in space, is to see what it looks like in space. And so I use the images from different spacecraft around the solar system to kind of answer that question. And so between high school and college into graduate school, that's sort of how I decided to go to become a planetary scientist more broadly. Yeah.
Where's your current research focus?
Cool. So my current research focus is in a couple of areas. One is in doing geologic mapping on the moon. Now, what that means is that I take images taken by NASA's Lunar Reconnaissance Orbiter. They're looking straight down on the surface of the moon, and so we've got photographic maps of the entire surface of the moon now. And geologic mappers, what we do is we try to group similar looking ground with other similar looking ground. So maybe there's one type of ground that's covered in lots of little impact craters all over the place. And we'll call that one type of geologic unit. And I'll draw a line between that, maybe it's a squiggly line between that and maybe a lava flow. The moon has actually had lots and lots of lava flows. They look like lava flows in Iceland or Hawaii. And so I'll draw a line to kind of demarcating the boundary between there. Then I literally choose a color and I color in that type of ground. But I do that for these huge areas of the moon. And what that does is it simplifies the overall picture of what the moon looks like. And we geologists use those geologic maps in a very similar way to how an investigator, and maybe a police department, has to conduct forensics. something happened, there's clues all over the place, and you have to piece together the different clues to reconstruct what happened in the past. Geology is a forensic science. It's a natural forensic science. Asteroid impacts, volcanoes, moonquakes or other planet quakes, on Mars, water or wind. These are all things that happened sometime in the past, and they left their mark on the landscape. And if you learn to read the language of geology, you can piece together these clues and figure out what happened in the past to make the landscape look the way it does. So that's one thing that I do. But I also do laboratory experiments. I do experimental planetary geology. Now, some experimental geologists will make artificial lava. They'll take rock, they'll melt it, and they'll make artificial lava flows in the laboratory to understand lava flows. Other experimental geologists will make artificial minerals, and they'll look at them under a microscope, what's called a petrographic microscope, to see how the crystals grow together. What I do is I study impact cratering. When a meteorite or an asteroid slams into the surface and it digs a big hole in the ground, it excavates all this rocky debris. It comes out. We call it ejecta because it gets ejected out of that crater. And so I use laboratory equipment to simulate the scooping out of ejecta. So I literally have a catapult. It's a catapult like this. It's sort of like a giant mousetrap, and it launches sheets of gravel or sand, or sometimes even like crushed chalk, like colored sidewalk chalk that you might go draw on the sidewalk with. We take that, we crush it, and we see how that erodes. It runs out on the landscape, and how it changes the surface. We call this landscape evolution. But what's really cool is that sometimes I get to do those experiments in reduced gravity. So we have an airplane that flies at a bunch of climbs and dives and climbs and dives. And for 20 or 25 seconds, every time the airplane does that, we can have zero gravity. We can have moon gravity, which is 17% of Earth gravity. We can even have Mars gravity, which is 38% the gravity of Earth. And so we can see how changing gravity acts like a variable to change the landscape modification. And so then we use GoPro cameras and we record everything that happens, and we measure the amount of erosion. And a lot of this is inspired by Earth geologists who create artificial landslides on mountain slopes. And so they'll actually set up artificial landslides to study how all that mud and debris slides down a mountain and erodes. And on Earth, that's important for understanding hazards, because some people live close to mountain slopes, and landslides can take that out. So, Oliver, to answer your question in a nutshell, I do geologic mapping around the solar system, but especially on the moon, and I do laboratory experiments to better understand how impact craters form and modify the landscape.
I like the way how you gave the example of it being like investigating and looking for clues. I like that.
Oh, thanks.
My next question is, you specialize in geologic mapping and lab experiments aimed at understanding impact cratering, ejecta, landslides, and lunar mining. And what is the most challenging stage of conducting a research project?
Oh, what's the most challenging stage of doing a research project? Probably getting the funding to do it in the first place is pretty hard. Here in the United States, we have to write proposals to NASA to win grant money. And if NASA likes our grant proposal and they decide to give us the money, then that's great. And that money is important because it literally pays our salary and pays our health insurance and important grown-up things like that. And so I would say writing and winning those grant proposals is very hard, and you lose a lot. You don't win a lot of proposals that you write. So that's hard. Another thing that's hard, and I wouldn't say it's like actually doing the experiment. You know what? Actually, that's more of like a creative challenge than it is difficult, I would say. When you're an experimental scientist, it's a lot of similar creative type of thinking as what an artist might have to think through. It's like, okay, I'm trying to get at this goal, and I've got all these tools at my disposal, and sometimes you have to think about, okay, I've got this tool designed to do this. But in the words from the movie Apollo 13, I don't care what something was designed to do. I care about what it can do. What are some creative, innovative ways to use, I don't know, hammers or buckets of sand or vice clamps or whatever? What are some innovative ways to get at solving the problem. And that's a very creative type of problem solving that I really enjoy. Another, what for me is difficult is in science, when we've done our experiment or we've made our observations, we have to write it up into a paper. It's like you never it's like being in school forever, which might sound like a nightmare to some people. But in science, what good is it if you make a discovery, but you don't ever tell anybody? Like, it's not a science isn't a secret. We're out here to tell the world what our discoveries are. And the way scientists do that is that we write in journals. We actually write articles. They're called papers or articles, and they go through very heavy editing. And we call it peer review because it's reviewed by people who are your peers, your equals in science. And the point of that is to make sure that only the highest quality science gets published for the world to see. And so getting through the peer review process, you submit a manuscript, you've worked really, really hard on it, or you submit a paper, and it comes back. It's like if you've submitted an assignment to your teacher and it comes back with all this red ink, like redo all of this, and that can be discouraging sometimes. But making sure that you clearly communicate sometimes very difficult ideas or concepts is also a challenge in being a research scientist. I like that question. It was about what's the most difficult. Thank you for the question.
So, how did you become involved with the Planetary Society, and what does your role involve?
So to be clear, so the Planetary Society is a space interest group. I work for the Planetary Science Institute. Did you intend that?
Yeah.
Okay, yeah, it's a common. We're two friendly organizations. We get along well, but we have different functions and roles. So, so I did my graduate work. I did my PhD at Johns Hopkins University in Baltimore, Maryland, USA, and I did the research for that at a place called the Johns Hopkins Applied Physics Lab, or APL. And it's actually not located in Baltimore. It's down the road about 45 minutes, halfway between Baltimore and Washington, D.C. And so I did my research there. By the way, APL builds and flies spacecraft for NASA. So APL built the spacecraft that flew by, for example, Pluto. APL built Parker Solar Probe that's swinging very close to the sun and investigating it. So I did my research there. And then after my doctoral work, I stayed on as what's called a postdoctoral research fellow. So I stayed on at APL for 5 years. And during that time, I wrote grant proposals to NASA. I won a lot of my own funding. And then the time felt right to do two things: to start my company, Planetary Experience Consulting, planetary.space, and to also move over to the Planetary Science Institute, where I could focus even more on the science. One thing that planetary scientists spend a lot of time on, especially if they're at a place like APL or maybe NASA JPL or NASA Goddard or maybe somewhere at ESA, is they spend a lot of time working with engineers designing and building the next spacecraft or the next cameras or spectrometers or instruments that we fly in space. And that's good and fun and important. And I've gotten to do that for the NASA New Horizons mission. I've done that for other mission concepts. But the time felt right to really focus on the actual science, the images coming back from these spacecraft. And so I moved over to the Planetary Science Institute to give myself a little bit more freedom to run my own company, PlanX, but to also spend more time really diving into the guts of the science.
Thank you.
Oh, let me also add one other thing. The Planetary Science Institute, we're 130 scientists, and most of us work all over the country or all over the world. We're headquartered in Tucson, Arizona, USA, and a lot of people do work right there on site. But like I live in Washington, D.C. I can just take my laptop anywhere and work from there. So most of us work remotely, and that kind of flexibility is also really nice.
Thank you. Why are planetary scientists interested in impact craters, and what do they tell us about our solar system?
I love that question. So impact cratering is the most common and prolific geologic process in the solar system, because in the solar system, everything's running into and hitting into everything else. So if you look up at the moon with a pair of binoculars, or better yet, a small telescope, pretty much all you'll see are craters of all different of all different sizes. You'll see craters inside craters, inside craters, inside craters. And so they are the most, it's other than volcanic eruptions come behind impact craters, but impact craters are the most common way that a planetary landscape changes over time. And so since impact cratering is the most important geologic process because it controls what the landscape looks like, it garners a lot of attention. to understand all of its different facets. And for Earth, understanding impact cratering is especially important. So Earth and pretty much all the planets are about 4.5 billion with a B billion years old, and within the first billion years, impact cratering was much more prolific and commonplace than it is now, because there were still a lot of asteroids left over from the formation of the planets. So as impact craters, so the early Earth got hit even more than the moon got hit. It's just that most of our craters have been erased from life, water, and plate tectonics, all of which are lacking on the moon. And so impact craters, even though they're devastating and they're violent, over the long term, they can actually become habitats for microorganisms to get a foothold, because it fractures the ground, it heats it up really hot, but then as it cools, the water, groundwater, can move through all those newly created fractures. And you've got an energy source in the hot rock. Rock is also the form of nutrients for microorganisms, and you've got water. So it's this really great nursery for early life to maybe get a foothold. So impact craters are very important for understanding early Earth, because we're still trying to figure out how life started on this planet, and maybe how life can start on other planets. And impact cratering is just one of the most fundamental processes in planetary geology. So it controls a lot, it's dominant, and so it generates a lot of attention to try to understand it better. And there's still a lot we don't know about it. It's like, yeah, so one thing hits something else and digs a hole in the ground, but there's some really interesting physics. There's some very interesting geology. Literally, the minerals change when they get under extreme pressures like that. So there's a lot we still don't understand, and so that's why we're still researching it.
In your opinion, what is the most exciting aspect of your career?
Ooh, thanks, Oliver. That's so. What I love more than anything is to see strange new worlds up close for the first time. See real seat of your pants exploration. Before we started recording, we were talking about astronaut Al Worden, who was on NASA's Apollo 15 mission to the moon in 1971. And one of his crewmates, actually the commander of that mission, Dave Scott, who got to walk on the moon while Al orbited the moon overhead, he got off on the surface of the moon after landing. He said, "Man must explore, and this is exploration at its greatest." And I really agree with that. I mentioned earlier that I was privileged enough to get to be on the New Horizons mission. That's still the only spacecraft to have ever visited the planet Pluto. And I'm not here to argue whether you think it's a full planet or not, but it's still a fascinating world, hanging out on the hairy, icy edge of the solar system. And growing up, being fascinated about space, we didn't know what Pluto looked like. Even the Hubble Space Telescope showed it as a fuzzy dot in the sky. And it wasn't until July 15th, 2015, when I was doing my PhD at Johns Hopkins, that we got our first up-close images from the spacecraft to show us what it looked like. And, I mentioned that one of my motivating factors for being a planetary scientist is to answer the question, what is it like in space? And what it looks like in space is one of the things of what it's like to be in space. And so getting pictures back of Pluto for the first time, showing us finally what Pluto looked like, that was the most exciting seat of your pants exploration I could hope for. On the flip side, I love human spaceflight, especially when humans go to the moon, because they get to answer because they are telling me what it's like in space, not just what it looks like, not just what the gravity feels like, but what their emotions are. And so that's not the planetary science, but it's the human side of spaceflight. A robot can't tell you what emotions they feel when they're on the moon, but a human can. And they're also seeing a landscape from an astronaut on the moon, even though we've imaged that spot from above, from orbit before, but we've still never seen it from a human perspective. And so that's still a little bit of seeing strange new worlds for the first time. And when I was in university, at Houghton University, I loved watching the pictures come back from the Mars rovers and from the Cassini orbiter orbiting Saturn. And that was also kind of seat of your pants, strange new world exploration, because Saturn has all these moons. It's got 7 round moons, like small planets orbiting Saturn, and getting to see what those small moons looked like up close from different angles, and got to get at that question. So that's really exciting too. I've got to work on a couple mission concepts. These are not spacecraft that flew, but when I was at APL, these were we got teams of scientists and engineers together to work out what the next missions could be. One of those we called Neptune Odyssey. and it was to send a spacecraft, a robotic spacecraft, to orbit the planet Neptune, a giant planet, the same distance from the sun as Pluto, 3 billion miles, 5 billion kilometers, 30 astronomical units, same distance from Pluto, but it's a giant planet, and it's got this very strange moon called Triton, which is a twin of Pluto that got captured into orbit. Triton used to be its own dwarf planet until Neptune stole it to become one of its moons, and it's in this really wonky orbit around Neptune. And so getting to design a spacecraft mission and what cameras should be on it and how close should it fly by Triton and Neptune. And oh my goodness, it's going to take 17 years from launch to when we actually get to Neptune. So you have to be patient. So that's been really exciting because and that's a way to answer the question, what's it like in space? So those are some exciting highlights I've gotten to be involved with. Thanks for the question, Oliver.
Thank you. I'd just like to mention that Al Warden was the former patron of MajorTim.space until he passed away in 2020. But my next question is, what would you say has been the most groundbreaking discovery in planetary science during the last decade?
During the last decade, most groundbreaking. I'm going to say part of it is the exploration of Pluto for the first time, seeing what an icy dwarf planet looks like. You know, there's 8 big planets in the solar system if you count Mercury on the small end of big, but there's 130 Pluto-sized planets out beyond Neptune. Overwhelmingly, icy dwarf planets are the most common type of planet in the solar system, and we've only been to one, Pluto, and actually its moon, Charon. But so I would say just seeing what a dwarf planet looks like up close for the first time has been groundbreaking. You said the last decade. That takes us back to 2015. So that's like right at the edge there. One really big deal discovery recently, just this past year in 2025, was the Mars rover Perseverance discovery of a rock on Mars that if it were on Earth, we would say that it formed in like a bog or a swamp with microorganisms doing something in the dirt, in the soil. And I'm not an astrobiologist, so this is speaking a little bit outside my area, but we don't know exactly how to make that type of rock without life. So that should be a strong motivator for going to Mars and bringing samples back to Earth so that we can study them in more detail here in the laboratory. So that is sort of still a to be determined, a TBD discovery in planetary science, how big of a deal that is. Let's see. I want to think of one more in planetary science. 2015 till now has been a little bit of a quiet period in planetary science, really since the end of the Cassini mission in 2017. Because the Cassini spacecraft was deorbited into Saturn to protect the Saturnian environment so that the spacecraft wouldn't crash on Enceladus or something and contaminate it. And we've had some flybys of other places since then, but it's been a quiet time, and that's going to pick up again in the late 2020s and early 2030s when spacecraft get to Jupiter's moons Europa and Ganymede, and to the planet Mercury again, and to the giant metallic asteroid Psyche. So we're in a quiet period right now, and so yeah, I'm gonna kind of leave it at that. I think of some really big deal discoveries on. Oh, actually, one other thing is some Chinese spacecraft returned samples from the moon for the first time since the Soviets did in 1975, and we're starting to get better ideas of how old some of those big craters are on the moon. And understanding how old the moon's craters are can tell us how old or how often Earth got hit by asteroids in its first billion years. Because the moon records those impact craters way better than Earth does, because the moon doesn't really erase craters like Earth does. And so we like to say that the moon is Earth's attic. It's got all of our baby pictures. It's got all of our like trinkets from when we were kids. And if we want to learn about early Earth, the only place where that geologic record is preserved is on the moon. So so some of the Chinese missions that have returned samples from the moon have been some pretty big deals. Like they've been able to tell us how old the South Pole Aitken Basin is, the largest impact basin, not just on the moon, but in the solar system. So that's been a big deal.
Can you pinpoint a particular moment in your career that stands out as the most memorable, and why?
Yeah, a couple really memorable times are when I was a graduate student and we flew by Pluto. I remember. So yeah, I mean, as far as I know, I got to be the first person to discover mountains on Pluto. And I mean, that was really exciting. I was the only person in the room without a PhD. I was the only graduate student in the room. This was a room, it was a converted conference room at APL. And we were, I think, 2 days past closest approach to Pluto. The spacecraft just flew by Pluto on the way out of the solar system. And so, and it took a long time to send images back. So I think this must have been July 17th, 2015. And we were getting our first like really zoomed in pictures, not just seeing all of Pluto as a round planet, but really zoomed in, little, like I call it postage stamps, pictures across the face of Pluto. And the first of those had come in, and it was on my colleague Ross's giant computer screen. And it was this big white plane. It was really bland looking. We now know it's a nitrogen ice glacier on Pluto called Sputnik Planitia. But at the time, it was mostly white with a few cracks through it. And everyone's looking at that. But I knew that another picture was queued up and was coming back to Earth from the spacecraft. So I'm typing commands into my computer to download that next image. And it started to download, and I got about 2/3 of the picture, and there's a black bar at the bottom because the picture hadn't fully come back from space yet. I mean, it was like a brand new picture. And I'm looking at this view of Pluto, and I'm seeing these big, jagged peaks coming up at the camera. And I'm looking at this, and it's like the Himalayas or the Rocky Mountains in the United States or Canada. And it's like looking down on mountains. If you've ever flown over mountains in an airplane, it looked like that. And I'm looking at this, and no one else is looking at my computer. No one else has this picture up on their computer. Everyone's looking at Ross's computer screen with that white nitrogen ice glacier. And so I'm like, guys, there's mountains on Pluto. Everyone ignores me. I'm the only one without a PhD in the room. No one's paying attention to me. And I'm like, guys, there's mountains on Pluto. And then finally someone turned around and said, hey, look at Kirby's computer. There's mountains on Pluto. And so, I mean, that was just exciting. That was like seat of your pants exploration, seat of your pants science. It's when there isn't even a hypothesis to test in science. It's called a fishing expedition. It's like, what's there? I don't even know. It's a kind of science infants do when they just open their eyes and just take in the world for the first time. It's that kind of discovery in science. So that stands out. I will say another thing that really stands out is the first time I got to go on a zero gravity airplane flight. I've wanted to be an astronaut my whole life, still haven't made it. But, you know, getting to float around in weightlessness or experience the very light moon gravity that's on the moon. I've gotten to experience that now 23 times on 23 different airplane flights. And so my first airplane flight, and I've done research experiments on there. I've helped other people do their research experiments. That's been a dream come true, to get to experience the weightlessness of space that astronauts get to experience. So that, furthermore, even though I've never been to space yet, hopefully, that still answers the question a little bit, what's it like in space? So thanks for the question, Oliver. Those are so discovering mountains on Pluto, seeing Pluto up close for the first time, and getting to experience weightlessness are two of the career highlights for me.
Also, what do you hope to discover in your research?
Ooh, what do I hope to discover in my research? I am really interested in how impact craters, how craters of different sizes form. So you're probably most familiar with the very basic type of impact crater, these simple bowl-shaped craters. But when craters get to a certain size, and you can see this if you point your telescope at the moon, you'll see a lot of craters with a mountain peak right in the middle. And instead of having nice, gently sloping crater walls, you'll see these stair steps going down into the crater. They're this terracing. Those are called complex craters, and we don't know how they form. But for craters larger than about 20 kilometers or 12 miles on the moon, they actually begin, you know, if you drop a rock in water, you'll get that bowl-shaped splash, and then sometimes you'll get that splash that jumps up in the middle of that. Pay attention next time you throw a rock into a pond or something. Well, we think the same thing happens with solid rock. The rock will splash back up in the middle of the crater, but then it's like, wait a second, I'm a solid rock. I'm not supposed to splash. And it'll freeze in place as a mountain. And you see this all over on the moon. And so I'd like to help discover how that happens. We think there's a process called acoustic fluidization, big science word, that just basically means the ground is vibrating a lot, and that vibration makes the solid rock flow, or actually broken up chunks of rock flow kind of like a liquid. So I'd like to help discover more of how that works. I'm actually writing a NASA grant proposal right now to help us figure that out. And I'd also like to discover more places with my geologic mapping. I'd like to discover more places that we might eventually want to send either astronauts or robots to tell us, to sample rock that used to be molten in the heat of the impact. So those are some discoveries I'd like to help make.
I'd like to go up in a plane and experience weightlessness. It sounds really fun.
Ellie, I hope you get a chance to do it. And
Thank
Oliver,
you.
you too, if you're interested.
This is our final question.
Okay.
What advice would you give to anyone looking to pursue a career in planetary science?
Yeah. If you want to have a career in planetary science, it's first of all perseverance. If you want to be an actual scientist, go to university, go to a doctoral degree. Be willing to study outside of your native country, because some of the best programs are across Europe. They're in the United States. They're in Canada. Some are in Australia. Other places in the world. So be willing to relocate. I'm from Michigan. I had to go to Baltimore, Maryland, to do my doctoral work. Some people have to go to a different country. So be willing to do that. Be willing to work hard. And if you find an area that you're not good at, like I'm really not good at math and physics, but I'm pretty good at geology. So be willing to pivot, to change directions a little bit to still kind of get towards your goal. But I also want to say that there's lots of jobs in space exploration that don't require a doctoral degree or a master's degree. We need engineers. We need technicians. We need electricians, welders, pipe fitters. We need accountants and managers. And just because you don't major in college or in graduate school in a space field, you can still work in the space industry regardless of your skill set. You might really love number crunching and you're a really great accountant, but you love space on the side. Well, you can combine those and you can go work for ESA or NASA or work for a university department that does a lot in space exploration. Like in the UK, Milton Keynes Open University, Imperial College London, different colleges at Oxford and Cambridge all have great space science programs, including planetary science. So those are departments you can go work in or be a student in. So there's even, just in the UK, there's a lot of opportunities.
Thank you so much for speaking to us. I've really enjoyed it.
It's my pleasure, Ellie and Oliver. Thank you for your interest.